Welcome to Process Piping Hub. Today, we're diving into the fascinating world of industrial boilers, powerful systems that keep factories running, process industries operating, and energy flowing. We'll explore different types, from fire tube to water tube, and cover package boilers to fluidized bed systems. Together, we'll break down how each one works and where they're used. So let's heat things up and get started. Let's take a closer look at the different types of industrial steam boilers. In this slide, I'll give you an overview of the main designs, how they operate, and where they're commonly used. Understanding these variations is crucial because each type has unique advantages and is suited for specific applications. As we go through, I'll highlight the key principles behind each design so you can see how they fit into the broader picture of industrial steam generation. This will help us appreciate the importance of choosing the right boiler for the right job, which is a central theme of today's presentation. When choosing the right boiler for an installation, it's essential to consider the specific requirements for steam type, pressure, and output. While some capabilities can overlap between different types, the particular application often determines the most suitable choice. Let's start with the coil steam generator, also known as a once-through boiler. In this design, water is heated inside a continuous tube coil, which allows for very rapid steam production. This makes it excellent for applications that need quick startup times and consistent steam quality. Next, we have the water tube boiler. In this type, water is contained within tubes that are heated externally by fire. These boilers are typically used where very high pressures and large outputs are needed, such as in power stations. Their design allows them to handle extreme conditions efficiently. Finally, the MTHS, or fire tube boiler, is also called a smoke tube or shell boiler. Hot combustion gases pass through tubes that are submerged in water, transferring heat to produce steam. These are commonly used in smaller industrial processes and are valued for their simplicity and reliability. Connecting this to our overall theme, selecting the right boiler isn't just about matching equipment to immediate needs. It's about understanding how each type's design influences performance, efficiency, and safety in your specific application. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the water tube boiler and how it operates. This design was actually patented back in 1867, and it works by injecting water into a lower drum. From there, the water flows upward through tubes that are heated by a furnace. As the water passes through these tubes, it boils, turning into steam. The steam then collects in an upper drum, ready to be used. This configuration is particularly significant because it allows for extremely high pressures and temperatures, which is essential for efficient power generation. Speaking of which, the primary application of these boilers is in electricity generation at power stations. Their ability to achieve high efficiency and operate at high temperatures makes them almost exclusively suited for this purpose. In fact, they account for about half of the world's electricity production, highlighting their critical role in our energy infrastructure. So, in the context of our overall presentation, understanding this design helps us appreciate how advancements in boiler technology have directly contributed to more efficient and sustainable power generation on a global scale. Now, let's take a closer look at the MTHS, or fire tube boiler. This type of boiler is quite common in various industries, and it's also known as a smoke tube boiler. The key idea here is that the combustion products, or the hot gases, actually flow inside tubes that are submerged in water within a larger shell. This design allows for efficient heat transfer from the hot gases to the water, producing steam effectively. Moving on to some key characteristics, these boilers typically operate at pressures between 6 and 18 bar. That's a range suitable for many industrial applications. They generally supply saturated steam, which is steam at the temperature corresponding to its pressure, making them versatile for different processes. Efficiency in these boilers is largely determined by the total surface area of the heat transfer tubes. The more surface area, the better the heat transfer, and the higher the efficiency. That's why design features like the 3-pass wetback and reverse flame boilers are popular. They maximize heat transfer by improving the flow of gases and heat exchange. Overall, these boilers are well suited for applications requiring reliable, steady steam supply, and understanding their design and operation helps us appreciate their role in industrial settings. Let's take a closer look at the MTHS boiler rating, which is expressed as F and A 100 degrees C. This means from and at 100 degrees Celsius. Now, this rating measures the evaporative capacity of the boiler, not the actual steam output. In other words, it tells us how much water the boiler can turn into vapor, based on a certain amount of energy, rather than how much steam it produces directly. For example, 1 kilogram per hour of F and A at 100 degrees C corresponds to about 2257 kilojoules per hour, or roughly 627 watts of net heat release. That helps us understand the energy involved in the process. Interestingly, this standard actually originated back in the 19th century. Despite all the technological advances since then, it's still used today as a common way to compare boiler capacities across manufacturers. So remember, when you see a boiler rated as 1000 kg/HRF and A 100 degrees C, it's not saying it produces exactly that much steam. Instead, it's indicating its evaporative capacity or how much energy it can release to turn water into vapor. This historical standard gives us a consistent way to compare boilers, even after all these years. Let's take a quick look at the boiler comparison at a glance. Starting with the coil steam generator, its main principle is water in the tube, which makes it quite simple in design. It's typically used for infrequent process steam needs, and because of its compact footprint, it's ideal where space is limited. Moving on to water tube boilers, these operate on the same principle of water in the tube, but they can handle very high pressures, even up to supercritical levels. This makes them suitable for large-scale power generation, though they tend to have a slower startup time and a much larger physical footprint. Finally, the MTHS, or fire tube boilers, have fire in the tube as their core principle. They operate at medium pressures, generally between 6 and 18 bar, and are quite versatile for various industrial processes. However, they tend to be larger in size and have a moderate startup speed. Overall, the choice of boiler really depends on the specific application, pressure requirements, space constraints, and how quickly you need it to start up. Each type offers different advantages tailored to different industrial needs. Let's take a moment to understand boiler plants, focusing on two key systems: low-pressure boilers and combined heat and power, or CHP, systems. These systems are essential in providing efficient energy solutions in various settings. Low-pressure boilers are typically used for heating and hot water applications, operating at lower pressures to ensure safety and simplicity. They are straightforward but still highly effective for many building needs. On the other hand, CHP systems are a bit more advanced. They generate electricity and useful heat simultaneously, making them highly efficient because they utilize fuel more effectively. This dual functionality not only reduces energy costs, but also minimizes environmental impact. Recognizing the differences and applications of these systems helps us appreciate how they fit into the bigger picture of sustainable and efficient energy management. Throughout this presentation, understanding these boiler systems will be crucial as we explore how to optimize energy use and reduce operational costs. Today, we're looking at low-pressure boiler plants, which are essentially the workhorses of many boiler houses across Europe. These systems are known for their reliability and widespread use. They typically utilize shell boilers, also called fire tube boilers, which are well suited for steam pressures up to 25 bar and capacities reaching up to 25 tons per hour. These specifications make them ideal for a range of industrial and heating applications. Now, as we move forward, let's delve into the key components that make these boilers function efficiently and safely. Understanding these parts will give us a clearer picture of how low-pressure boiler plants operate within the larger energy system. Let's take a closer look at the core components of a low-pressure plant. First up is the steam boiler, specifically the shell or fire tube type. This is essentially a cylindrical shell that contains furnace tubes where combustion takes place. Water surrounds these tubes, and as the combustion occurs, it heats up and turns into steam. Sometimes, a superheater is added to this setup, which heats the steam above its saturation temperature, making it more efficient for power generation or process use. Next, we have the deaerator. Its main function is to remove corrosive gases like oxygen and carbon dioxide from the feedwater. It does this by heating the water with steam, which helps prevent corrosion in the boiler and the piping system, an essential step to prolong equipment life and maintain efficiency. Finally, there's the economizer. This is a heat exchanger installed in the chimney. Its job is to recover residual heat from the hot flue gases, which are typically around 220 degrees Celsius. The recovered heat is then used to preheat the feedwater before it enters the boiler, which can save around 4 to 5% in fuel consumption. These components work together to improve efficiency, safety, and longevity of the plant, all while supporting the overall goal of optimizing energy use in low-pressure systems. Now let's take a closer look at the flue gas condenser. It's installed right after the economizer, and its main job is to cool the flue gases even further. By doing this, it condenses water vapor present in the gases, which releases additional energy, specifically the enthalpy of evaporation. This recovered energy is then used to preheat the makeup water, improving overall efficiency. Next, we have the softener. Its role is to remove hardness ions, mainly calcium and magnesium, from the makeup water. Why is this important? Because if these ions are left in the water, they can cause scale buildup inside the boiler tubes. Scale reduces heat transfer efficiency and can even lead to dangerous overheating, so keeping the water soft is critical for safe and efficient operation. Finally, let's discuss the condensate vessels. These vessels collect the condensate that's returned from the plant. Some of this condensate has been exposed to the atmosphere and absorbed oxygen, which can cause corrosion. Therefore, this oxygen-rich condensate is sent to the deaerator for treatment, ensuring that the water going back into the system is clean and free of corrosive elements. All these components work together to enhance system efficiency, protect equipment, and maintain safe operation throughout the plant. Now, let's talk about blowdown and water quality control. When steam leaves the boiler, impurities tend to stay behind and become more concentrated in the water. To keep the water within acceptable purity levels, we use a continuous blowdown process, which involves an automatic valve that drains a small amount of this concentrated water. This process is often controlled based on conductivity, which helps us monitor the purity effectively. Next, we have the blowdown flash vessel. High-pressure blowdown water is directed here, and as the pressure drops, it creates what's called flash steam. This steam is clean and can be recycled back to the deaerator, which improves overall efficiency. The remaining hot water from this process can also be used to preheat the feedwater, helping us recover valuable energy and reduce fuel consumption. Finally, there's the bottom blowdown. This is a manual process where a valve at the bottom of the boiler is opened briefly each day to discharge sludge and dirt that has settled at the bottom. Unfortunately, the heat generated during this process usually isn't recovered, so it's an area where we might look for potential improvements in energy efficiency. All these methods work together to maintain water quality and optimize boiler operation, which ties back to our overall goal of safe, efficient, and sustainable steam production. Now, let's take a closer look at the combined heat and power, or CHP, boiler house. When we need high pressures and large steam outputs, water tube boilers are the go-to choice. These boilers are specially designed to handle the demanding conditions of a CHP system. The key advantage here is that they produce steam not just for various industrial processes, but also generate electricity simultaneously. This dual function significantly boosts overall efficiency because we're making the most out of the fuel used. Instead of just producing heat or steam alone, the CHP setup allows us to recover and utilize energy more effectively. By integrating the boiler with power generation, we're optimizing energy production and reducing waste. This approach is a critical part of modern, sustainable energy solutions that we're exploring throughout this presentation. Water tube boilers are a high-pressure solution, and they work a bit differently from other types of boilers. In these systems, water actually flows inside the tubes, while the combustion process takes place in a furnace that surrounds those tubes. This design is especially useful for generating high-pressure steam needed for power plants. Another key point is that these boilers are almost always paired with a superheater. The superheater heats the steam further, making it more efficient for electricity generation. Now, when it comes to how water circulates within these boilers, there are a few main methods. First, there's natural circulation. This relies on convection, meaning hot water rises while cooler water falls, creating a natural flow between the upper and lower drums. Next, we have forced circulation, where a pump actively moves the water through the system. This ensures a consistent flow and better heat transfer, especially in high-pressure situations. Finally, there's the once-through method. In this case, water is pumped through the piping system in a single pass, without recirculating. This approach can simplify the system and is often used for very high-pressure applications. So, to sum up, water tube boilers are versatile and efficient, with different circulation methods to suit various operational needs, all crucial for reliable and high-pressure steam generation. Let's take a closer look at how steam turbines work, starting from pressure to power. High-pressure superheated steam is directed through a nozzle, where its pressure energy is transformed into high-velocity kinetic energy. This rapid, high-speed steam then strikes the turbine blades, and it's this impact that causes the turbine wheel and shaft to spin. As the shaft turns, it drives a generator, producing electricity. That's the core of how we convert thermal energy into electrical energy. Now, because steam pressure decreases as it expands, we typically use multiple stages of turbine wheels. These stages allow us to extract energy more efficiently, ensuring we maximize power output even as the steam's pressure drops and its volume increases. This multi-stage process is what makes steam turbines highly effective for generating large amounts of electricity in power plants. It's a beautifully coordinated process that connects the initial high-pressure steam to the final electrical power we rely on every day. Let's take a closer look at comparing different types of turbines. First, we have back-pressure turbines. These are mainly used in combined heat and power systems, or CHP. In this setup, the exhaust steam isn't wasted. Instead, it's reused as process steam for heating or other industrial purposes. This dual use allows these turbines to generate electricity while simultaneously providing useful heat, which makes the overall system very efficient, around 85% efficiency overall. On the other hand, we have condensing turbines, which are primarily found in power stations. These turbines work by condensing the exhaust steam in a vacuum, which maximizes the amount of electricity generated from each ton of steam. However, because they don't utilize waste heat for other purposes, their overall efficiency tends to be lower, typically between 40 and 50%. They are optimized purely for electricity production, making them ideal for large-scale power generation. So, the key difference here is that back-pressure turbines are more versatile, combining heat and power, which boosts their efficiency, while condensing turbines focus solely on maximizing electricity output, though with lower efficiency overall. Connecting this back to our overall theme, understanding these differences helps us choose the right turbine type based on whether the goal is combined heat and power or just electricity generation. Now, let's look at an even more advanced combined heat and power, or CHP, setup that uses a gas turbine. The key idea here is that the hot exhaust gases from the gas turbine, which are rich in oxygen, can be utilized to generate steam. This is done in a waste heat boiler, which captures the heat from the exhaust to produce steam. By doing this, we're effectively recovering energy that would otherwise be wasted. This approach not only improves overall efficiency, but also highlights how integration of different technologies can optimize energy use. It really exemplifies the innovative strategies in CHP systems to maximize output and reduce waste, aligning perfectly with our goal of more sustainable and efficient energy solutions. Let's walk through the gas turbine CHP process. First, air is compressed, which increases its pressure and temperature, preparing it for combustion. Next, we introduce fuel into the compressed air and ignite the mixture, reaching temperatures between 900 and 1,200 degrees C. This high-temperature combustion produces hot gases that expand rapidly, driving the gas turbine and generating electricity. The hot exhaust gases, still around 500 degrees C, then pass into a waste heat boiler, where they generate high-pressure steam. This steam is used to drive a steam turbine, which produces additional electricity, making the process highly efficient. Finally, the exhaust steam from the steam turbine isn't wasted. It's used directly for industrial processes, adding value to the entire system. This multi-stage approach allows us to maximize energy extraction from a single fuel source by generating electricity twice and utilizing steam for industrial needs, highlighting the core advantage of combined heat and power systems. Let's go over the key takeaways from our discussion. First, boiler plants are absolutely critical for generating steam, which we use for both heating and power production. They form the backbone of many industrial processes. When it comes to low-pressure plants, they typically use fire tube boilers. These plants incorporate many essential components like deaerators and economizers, which are vital for maintaining efficiency and safety. Moving on to combined heat and power systems, or CHP. These systems utilize water tube boilers along with turbines to produce both electricity and process steam simultaneously. This setup allows for very high overall efficiency, making it a smart choice for maximizing energy use. Another important point is water treatment. Proper softening and demineralization of water are crucial steps. They help prevent damage to the boilers and ensure they operate at peak performance over time. Finally, in advanced CHP configurations, especially those with gas turbines, we see a highly efficient way to extract maximum energy output from the fuel we burn. Overall, these concepts are interconnected, emphasizing the importance of proper design, operation, and maintenance to achieve optimal performance in boiler plants. Thank you so much for being here today. I really appreciate your time and attention throughout this presentation. If you found the content valuable, I encourage you to subscribe for more updates and future insights. Your support helps us continue to share important information and grow this community. Once again, thank you, and I look forward to connecting with you again soon.